So we've just finished up talking about the property of inertia, how lazy an object is, how hard it is to get it to change what it's doing, either being at rest or in motion. And changing your at rest or in motion state is an acceleration. So clearly mass has an effect on acceleration. We also expect that how hard you're pushing or pulling, in other words, the force that you're putting on the object, is going to have an effect on its acceleration too. And in this lab, we're going to carry out two kind of mini experiments to test the effect of both of these variables. We have to consider them both to be separate independent variables that we're going to change. We want to see how they affect the dependent variable of acceleration. And what that means is that we're going to carry them out one at a time. So I want to show you the overall experiment that we're going to be doing, and then we'll talk about what the general strategy is for controlling first one variable and then the other. So the basic experiment we're going to have is we're going to have somebody pull another person down the hallway on this low friction cart. These are rollerblade wheels, so we can keep the force of friction as negligible as possible. We're going to be able to measure the force people are pulling because we've got this old fish scale, which can measure up to a 30-pound pull. So in one of the experiments, as we discussed, we'll be keeping the mass of the person constant and pulling with different forces. In the other, we'll do the opposite. We'll keep the force constant and we'll pull people of different masses. So I want to show what one such pull looks like. And my friend Mr. Sember helped me do it. Hang on one second. So Mr. Sember has volunteered to pull me, and he's going to pull me at a constant force of 10 pounds, and we'll see what constant acceleration looks like.
Whee!
So on the next slide, you're going to see some data from one of my classes of how mass affected acceleration, and then you'll see a graph, and we'll take a look at what that quality looks like. So I hope you can see how we're going to have a control over these variables. We actually have a whole class full of people, so we could have different people ride the cart, and we could also have one person pull the cart with different forces. Again, we can only change one independent variable at a time, or else we don't know what is causing the effect. So we're going to start by changing the mass of the person riding the cart and seeing how that affects acceleration. In order to control force, we're going to pull with 10 pounds constantly. So basically, we're going to get 5 or 6 people. We're going to have their weight and use that to get their mass. And then we're going to go back in the hallway. The hallways at our school are a lot like a football field. They're striped, so we can use that to figure out how far someone's traveled. And we can use a stopwatch to get time. So we'll just plug into our constant acceleration equation and we'll solve for acceleration. So by getting people's weight, the distance they travel and the time they travel, we get all the information we need to test mass versus acceleration. So here's our data for acceleration versus mass for one of the classes in the 2017-2018 school year. And you can see that both a line, which I drew in pink, and a curve actually could be described to fit the data pretty well. There's nothing that makes this obviously nonlinear. So what I had the class do was draw a best fit line and then discuss what would it mean to have this line cross the M axis here. Well, that would imply that when you had a large enough person, when your mass got to a certain level, your acceleration would suddenly become negative. So that would imply that if you had like something twice as massive as the largest object, that all of a sudden it would start accelerating backwards when the person grabbed the scale. And that clearly doesn't make any sense. As students in most classes pointed out, it would make sense that the bigger they got, the less acceleration they had, and that pattern would continue rather indefinitely. Usually a student pointed out that mathematically we would call that an asymptote. That zero acceleration we'd expect to be the most negative acceleration, and that the larger you got, the closer you get to it. So we went through graphs that could fit that pattern, and the hyperbola, which is sometimes called the rational graph, seemed to be the one that fit the best. Usually we think of that as y equals 1 over x, but it's really y equals any value over x. And usually we would abbreviate that any value with a k for constant. So on this graph, what we're seeing is that acceleration is equal to some number divided by mass. And that another way of saying that is that acceleration is proportional to mass. So that's one of the big ideas of this lab. And what it can be translated into is that as mass gets bigger, acceleration gets smaller. Because if you have a bigger number on the bottom of a fraction, that makes the overall fraction smaller. So to see the relationship between force and acceleration, we kept the same person on the cart and pulled them with forces between 4 and 12 pounds. Converted that to newtons and graphed it versus acceleration. And we saw a nice linear graph. And what that tells us is that as force gets bigger, acceleration gets bigger. They are directly proportional. So we have our two graphs. One is showing us that as mass gets bigger, acceleration gets smaller. So acceleration is proportional to 1 over m. One is showing us that there's direct proportionality. As force gets bigger, acceleration gets bigger. So if we combine those two ideas, we end up with the idea that acceleration is proportional to 1 over mass and force. So acceleration is proportional to force divided by mass. We change a proportionality to an equality by saying that there's some number k times f over m that must equal a. And there's data that can be collected, which we do in the college level classes, that shows that k is just equal to 1. And that leaves us with acceleration is equal to force divided by mass. So we got both the effect of F and the effect of M by doing two separate labs, and this equation shows the combination of those two ideas. It's a very powerful equation. It's usually written in the form F equals ma, and we can use it to relate motion, and specifically acceleration, to how hard we're pushing or pulling and the inertia of an object. It's a huge equation that we're going to use quite a bit.